Long wire. A long straight wire carries current I into the page. That's right over here. Point P is located at a distance r from the wire. What is the direction of the magnetic field at point P due to the current I? Using Amperes Law, develop an expression for the magnitude of the magnetic field at point P. Another wire with an identical current I is placed in parallel to the first one. So here's our new wire. What is the net magnetic field at point O, midway between the two wires? What is the net magnetic field at point A, located at distance y above point O? And if the direction of the left current is changed to out of the page, what is the net magnetic field at point A? What is the direction of the magnetic field at point P due to the current I? Using the right-hand grip rule, placing the thumb of your right hand in the direction of the current, which is into the page, right over here, and curling your fingers, you should find the magnetic field curling around like this. Okay? And it obviously keeps going out and out until you get to this point here, point P. And to find the magnetic field at point P, you take the tangent to that circle. So that would be in the down direction. So the direction of the field at point P points down. Using Amperes Law, develop an expression for the magnitude of the magnetic field at point P. Create an Amperian loop, right here in the dashed line, of radius r around the wire. The magnetic field is constant and parallel at every point to a line segment ds on the Amperian loop. Right? ds is going to be tangent to the loop wherever we find it, and b is in the same direction. That means that b dot ds can be replaced by just b ds. So we start with ampere. Our enclosed current is just I. We just have the one wire. We replace b dot ds with b ds. B is a constant. It comes out of the line integral. And then when you integrate all these little pieces of ds and add them all together, what do you get? You just get the circumference of a circle, which is 2 pi r. Do a little algebra, and here's our answer for the magnetic field at point P. What is the net magnetic field at point O? Well, we know the net magnetic field will be a combination of the magnetic field due to this wire and this wire. And that's what we have there. We have B net is equal to B left plus B right. The right-hand grip rule is used to find the direction of the magnetic field at that point. So we already did it for this guy here when we found it was in the down direction. Now we go here, and when we put our thumb, thumb going into the page, we find our fingers curling around like this. So at this point here, the tangent to that circle is up. So then we try and calculate the magnitudes of these. Well, we know that also. We did that in the previous part. It's just mu 0 I over 2 pi r. And then what we're going to say is we'll assign a positive value to the left magnetic field. Doesn't matter. It could have been negative, but we'll make it positive. So if that's positive, then B right is in the opposite direction, so that will be negative. We sum them together, and we get a net magnetic field at 0 at point O. So let me just erase all this so you can see it better. What is the net magnetic field at point A, which is located at a distance y above point O? We will construct Amperian loops for both wires, and we want that loop to intersect point A, right over here. Okay? The magnetic field due to each wire will be tangent to the loop. Then the net magnetic field will be the vector sum of the two fields. So let's look at the field due to B right. That's this guy here, the right current. And let me just erase this up here. We know that it will be tangent to the curve, to the Amperian loop at this point. And we also know it will be perpendicular, right, to a radius vector here that's coming from this wire, the right-hand wire. So B right will be in that direction. And then B due to this guy, now let's do it again. His magnetic field was going around like this, right? Into the page. Nope, got that backwards. It's going around this way. Okay, you put your thumb into the page, curl your fingers, and you get that direction clockwise. So at this point here, oh, you can't see that, so let me just erase. At this point here, it will be tangent to the curve, so it'll be in that direction. So that's our two vectors due to the magnetic field of each wire. Let's zoom in on point A now, and we've gotten rid of the left-hand wire because we don't have room for it. And we have our two vectors. This is due to the right-hand current, this guy. This is due to the left-hand current. And when we resolve them in the y direction, you can see that they have equal magnitude. They're opposite directions, they'll cancel out. But in the x direction, they reinforce each other. So we're going to have to add up those two. We are going to work now with the left-hand wire and find the magnetic field, B left, due to this wire. Going to do a little geometry here. We have this R here, okay, that's how far we are away from the y-axis, and we have y. So we have a triangle there, don't we? Okay, we have a right triangle. We would like to know what the value of this is because we'll put that into the equation for the magnetic field due to a wire. And we also have theta. That's going to be a big help here shortly. Here's the expression for the magnetic field around a current carrying wire. It's mu0I over 2 pi r. And notice we just put the big R in there. That's the distance from the wire to the Amperian loop surface. Let's talk about theta. Theta is this angle here, okay? And that means this angle here would be 90 minus theta. And since we have a right angle between the magnetic field and the radius vector, this angle here will be theta again. So let's put this in. We have B left is mu0I over 2 pi capital R. Now what is capital R? Well, we just use Pythagoras. That's the square root of the square of r squared plus y squared. And now it's time to get rid of some of this. Okay, so that's what we have here. Now we're just interested in finding the x component of that because the y component will cancel out with the y component of this wire. So if you look at this triangle here, bx is going to be left, right? That's what we just found here, times the sine of this angle. It's an opposite side there. So what is sine theta equal to? Well, let's go back to our original triangle. And once again, let me erase. A lot going on here. Sine is opposite over the hypotenuse. So it's going to be y over the square root of r squared plus y squared. We put that in there. We substitute in for B left, do a little algebra, and this will be our magnetic field in the x direction from the left-hand wire. You can work out B due to the right-hand current, and frankly I'd like you to give that a shot. Try doing the same geometry we did here for this guy, okay? Or, for now, we'll accept the symmetry argument where Bx left equals Bx right. So our net magnetic field, which is what we're looking for, is equal to both of them. You just multiply 2 times what we found on the previous slide, and you get this for our net magnetic field at point A due to both of these wires. If the direction of the left current is changed to out of the page, what is the net magnetic field at point A? So what we've changed is this guy right here. He's now coming out of the page. The magnetic field due to the right-hand wire stays the same. We didn't change anything. Same magnitude, same direction. The magnetic field due to the left-hand wire certainly keeps the same magnitude. You're still at the same distance from the wire, but its direction changes, right? Because if we take the right-hand grip rule, thumb out of the page here, we find our fingers curling around like this, and then at point A, you take the tangent, and there you go. So in this case, the x components of the individual fields have the same magnitude but opposite direction, so they sum to 0. The net field will be twice the magnitude of either wire in the y direction. We'll work with the left-hand wire again. Let's look at the geometry we have this time. We have this angle theta, okay, which means that this angle here is 90 minus theta. This angle here is now theta. And then since this is a right angle, okay, right, because magnetic field is tangent to the circle there, so it's perpendicular to the radius vector, this is 90 minus theta. And then we have this line like this. We go up here, and we find that this angle is theta. So I'm sure there's quicker ways of doing it with different math theorems, or you can just brute force it out like that. That's kind of fun. So in this case, the y component is going to be b left times cosine theta. So we start, frankly, we take some of the work we did on the previous page. That's our b left. Okay, actually that was a couple pages ago. And now what is cosine theta equal to? Here's theta. Cosine theta is going to be r over the square root of r squared plus y squared. Put him there. Okay. That's that. We multiply through. We get this expression. Now b net will equal to by left plus by right. So we just have to double this right here, multiply that by 2, and here is our b net, and it's in the y direction.